Okay, let's calculate inventory carrying costs. So previously we saw that the inventory costs are made up of these 4 types of inventory costs. And we're going to start by looking at how to calculate the inventory holding costs, also called inventory carrying costs. So the word holding and carrying is used synonymously. Okay, so let's see, what happens when you have inventory at a certain place. So this pile of boxes in the middle of the screen, assume that's some inventory floor stacked in a warehouse. Okay. Now, this customer demand, we're going to call it D, small d, and that's going to be in units per time period. So a certain number of units you sell per day or per week. And as you sell those units, inventory depletes. So you can see an arrow moving with the box moving towards the customers. So as customers, place orders, maybe it's an online retailer, they place orders online, they check out their virtual shopping cart, you have to ship those orders. And so the inventory goes down by D units per time period, small d, where D, small d, is the demand per time period. Okay, excuse me. Now, if you multiply small d by the number of time periods in a year, so let's say d, small d is per day, then you multiply by 365, or small d is per week, demand per week, so you multiply by 52 weeks in a year, or small d is demand per month, you multiply it by 12 months in a year. So you multiply it by whatever factor you need, and you can convert small d into capital D, which is annual demand in capital, which is capital D units per year. So I'm explaining what the different letters will mean when we get to the mathematical formulas, because in the formulas you'll see capital D, you'll see small d, things like that. So you need to know what these represent. So small d is demand in units per time period. Capital D is annual demand in units per year. And you multiply small d by number of periods per year, which could be 365 if small d is per day, or 52 if small d is per week, or 12 if small d is per month. So that's how fast our inventory is depleting this pile of inventory in the middle of the screen. Okay, at some point, this inventory analyst who has this red or black tie, the inventory analyst will look at the pile and say, oh, the inventory looks low. So it will call the supplier, yo, supplier, my inventory is low. Send me another batch of Q units, okay? So Q is the ordering lot size or batch size. Both terms are used for that, batch size or lot size. And so the supplier will have some processing time P, because the supplier may not have finished goods inventory ready to ship. If the supplier does have finished goods inventory, it may still take the supplier 1 day or 1 shift to create pallets or load the pallets, move the pallets to the dock to have them ready for the shipment. And so there's usually going to be some non-zero processing time by the supplier, right? The supplier may receive an order and they're in the middle of something and they may get to your order the next day, right? So there's going to be some processing time for your order. It could be 0, but usually it's going to be some positive number, okay? The units of time for processing time, like is processing time in days or weeks, has to match the units of small d. So you have to keep the same units. If small d is demand per day, units per day demanded, then you want to express the processing time in days. Okay, you can't have processing time in hours and have d in units per day, because then your formulas will not work. The units have to be consistent. After processing time of P, the items will be shipped, and then they will have a transportation time to get to you, which is small t, t days, or t weeks if the small d is in weeks, right? So same units. And then the lead time L of getting these items from the supplier will be P plus T, the processing time plus the transportation time, okay? When this order arrives, Q units arrive as a batch from supplier after L lead time days, then your inventory here will increase, it'll be replenished, and then you will not have low inventory for a while. And then as the demand consumes more and more inventory, then you have to reorder again Q units. So that's how inventory works. if you were to stand and stare at this pile of inventory, you'll see it go down, go down, go down, go down, go down. Again, hopefully before it hits 0, you'll see the replenishment order arrive, which will move it back up, and then it'll start going down again. Okay, and so if you plot the inventory level here in the warehouse, this pile of inventory, if you plot the level over time, you'll be able to see the famous sawtooth pattern. So if this is time, okay, and this here is inventory level, okay, inventory level, then you'll see you'll start somewhere to be going down, 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 and it'll jump up when it gets replenishment shipment, then start going down, 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 then jump up again, down, 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 jump up like that, right? So that's the sawtooth pattern of inventory level over time that you see because of this cycle happening, okay? So hopefully that explains why we get the sawtooth pattern, because inventory is depleted by demand at a rate of small d units per time and then replenished from the supplier, Q units, batches of Q units at a time. Now, we're going to look at another example of the same thing happening, okay? And this example is important because in this made-up example, we have no variability in the system. So we're saying demand is fixed. Every day we sell 1 carton because you can see day 1 to day 2, you're missing 1 carton. So 1 carton got sold on day 1. So day 2, you only have 5 cartons. Then another carton got sold. Day 3, you only have 4 cartons. Okay? So you are selling a carton a day. Your small d is 1 unit per day. Okay? Constant demand does not change. Every day you sell 1 carton of goods. Okay? Your lead time L is 3 days. So whatever processing time and transportation time the supply is there, the sum of P plus T, the lead time is 3 days. Okay? So if you are watching your inventory and day 1, let's say you have 6 pieces and you're selling 1 piece a day. So day 2, you'll have 5. Day 3, you'll have 4. Day 4, you'll have 3 pieces left. On day 4, any smart inventory analyst will say, I can project my inventory level into the future. Okay, I'm going to have 2, then 1, and then day 7, I'll have 0. So I better order now because my lead time is 3 days. So if I order today at the morning of day 4, I will receive the shipment on the morning of day 7. And let's say Q, your batch size or lot size is 6. So you will call up the supplier at the morning of day 4 and say, I have only 3 units left. Lead time is 3 days. So I'm going to run out on day 7. So please ship me something so it arrives on day 7. Okay. That's what you do. And ta-da. Again, there's no randomness in the system. Supplier lead time is 3 days. It's always taken 3 days. And so on day 7, we get a shipment which has 6 items. Okay? And then again, as we sell something on day 7, we're left with 5 items on day 8. So if there's no randomness in the system, demand is constant at 1 unit per day, lead time is always 3 days, then you will get a sawtooth pattern like the one shown in this picture with the red line going down at a constant rate, so going straight down, okay, like this, and then it jumps up, then goes down again. Obviously, because you order 6 units, it jumps up to 6, and because you sell 1 unit per day, in 6 days, it hits 0. So between 6 to 12, in 6 days, it's 0. And obviously, somewhere here on day 9, you place the reorder. So the reorder arrives on day 12. That's what's called this jump up. Okay. So if you have no variability in the system, this is what your inventory level over time will look like. The maximum point of this graph will be Q, the batch size that you order the inventory in. And the minimum point on this graph here would be 0. Okay. And so if you have triangles like this, these stable triangles, that going from between Q and 0, the Q being the peak, Q which is 6 being the peak, 0 being the bottom, then we know that the average level here will be the peak minus over 2 divided by 2, because half the time you're above this half level, half times Q, half the time you're below this half level. So the average is going to be the average inventory level. Average inventory level is called AIL. Average inventory level equals AIL equals Q over 2. Now this is a really important result. Okay, it seems really simple, but it's really important. Why? Because when you have no variability in the system, demand is constant, lead time is constant, then you don't need any safety stock. Safety stock protects against variability. If there's no variability, you don't need safety stock. So if safety stock is 0, okay, so safety stock equals 0, then what you have left is cycle stock. All you have is cycle stock. Cycle stock exists because you're ordering Q units at a time, not 1 unit at a time. Because you're ordering in batch of size Q. So cycle stock, when you order in batches of Q, leads to an average inventory level of Q over 2. So whatever is your batch size or load size or order size with your supplier, half of that is going to be your average inventory level due to the cycle stock. Okay. Okay, so in the real world, sales are variable. The small d represents the average sales per time period. So if small d is 10 units per day, some days you sell more than 10, some days you sell less than 10. Lead time may not be constant in real life. L represents, capital L, the average lead time. So if on average it takes you 2 weeks to get your product from the supplier when you order, sometimes it may take less than 2 weeks. Sometimes it may take 3 weeks or 2.5 weeks or 2 weeks and 1 day. So because, there could be delays, there could be the supplier just took longer, they were not ready. There could be some national holiday which shuts down the port for a day that didn't used to happen last time you ordered but happened this time, right? Any number of reasons. Lead time could be higher or lower. Actual demand that day could be higher or lower than the average. So if we order assuming fixed demand, okay, when D times L units remain, we may run out of stock before replenishment arrives. Remember that here in the previous slide, okay, we were ordering 3 days before we ran out of stock, because we know day 7 we're going to have 0 stock, because day 4, at the end of day 4, we have only 3 left. We know we're running out of stock. So how did we know on day 4 that day 7 is when we'll run out of stock? Well, we know that we need to reorder when we have D times L units remaining. D is 1, L is 3, so 1 times 3 is 3. So when 3 units are remaining, we better place the reorder so we can get the reorder exactly when we need it. The replenishment will arrive when we need it. Okay, so D times L is sometimes called the reorder point in the absence of safety stock. So if there's no safety stock, the reorder point ROP is called the demand during lead time, which is D, demand per day, times lead time L. And then you add to it the safety stock. But in this example, this is 0. So when safety stock is 0, reorder point is just D times L. Okay, so that's what's happening here. If we assume demand is fixed and lead time is fixed, and fixed lead time. So if we assume fixed demand, fixed lead time, that means we don't need any safety stock. That means the reorder point will just be D times L. If we assume that, but that assumption is not correct. In reality, demand is variable, lead time is variable, then we'll run out of stock before the replenishment arrives. So that is a very strong assumption that things are fixed, so we don't like to make that assumption. Okay, so to protect against this stock out, because things are not fixed, lead time and demand are not constant, they vary, we need to keep some stock, and that is called safety stock. Okay, so we saw that when we have no variability in demand or lead time, our inventory level over time plot looks like this. Its maximum value is Q, the batch size or the lot size, its minimum value is 0, average inventory level is Q over 2. When we add safety stock to deal with variability in demand and lead time, then the whole average inventory level over time plot moves up vertically by the amount of the safety stock. So on average, we are going to have the safety stock inventory there. On top of that, we'll have variations going from Q down to safety stock, then up to Q, then down to safety stock. So that sawtooth pattern, that part of the inventory level is called the cycle inventory. And then the remaining part, which is the inventory added to deal with variation in demand and lead time, so that when we place a reorder, if it doesn't arrive on time, or if there's too much demand while the reorder is in place, we don't run out of stock. That is called safety stock. So the average inventory level now, previously it was just Q over 2. Now the average inventory level, AIL, becomes Q over 2, which is the cycle stock plus the safety stock. Okay, so remember this part here is the cycle stock. Okay. The average of it, average cycle stock. Stock and inventory are used synonymously. So stock means inventory, so average cycle inventory. So this is your cycle, average cycle inventory, and then your safety stock that gives you your average inventory level. Now, carrying cost, also known as holding cost, is a function of the average inventory level. Average inventory level is going to be in units. So this is going to be, how many pieces of product you have. And then we multiply those units or pieces of product by a variable C, and then by a variable H. So we need to understand what are C and H. C is the landed cost of inventory at the location we are at. And we'll discuss this in more detail, but essentially what it means is that you have to pay for transportation as goods move across the supply chain. So at any location you're at, any distribution center, retail store, wherever you're at, you spend some money to bring product or goods to that place. And when you spend on transportation to move things along in the supply chain, at every stage that you store stuff, the cost at that stage includes not just what you paid the supplier, but also the transportation cost. So let's take a very basic example. Let's say, we are in a DC, distribution center, and our supplier is here, okay? And we pay the supplier $10 for an item, okay? We pay $10 to the supplier, $10, okay? So my writing is bad, just assume this is 10. And we pay $2 to move this unit, all the way to our DC. So the landed cost of this unit in our DC will be $12. Why? Because it has cost us $12 to get it here. 10 of those $12 went to the supplier, 2 of those $12 went to the transportation company, but it doesn't matter who it goes to. The point that we spent $12 to get it here means the landed cost is $12. So C is the landed cost. So depending on where you are in the supply chain, even for the same item, the C could be different. So at the supplier's loading docks, the C might just be the purchase price, what we pay the supplier. Then it moves across the supply chain. You keep adding transportation cost to landed cost. And at every facility along the supply chain, the landed cost is higher and higher. Now, holding cost or carrying cost is calculated for a stock in a particular location. So you're holding, because you're holding it in a particular location. So for that location, whatever the landed cost is, we're going to use that. When you multiply the landed cost by average inventory level, what you have here is the value of the inventory in dollars. This is the value of the average level of inventory in dollars. Okay, C times AICL. So when you have the value of inventory in dollars and you want to figure out how much do you have to spend to hold this inventory for 1 year, then you have this parameter called H, which gives you the holding cost per dollar of inventory per year. Okay. Now H is expressed in two ways. Okay. Sometimes we say H equals like a percentage, like 30%. Okay, and sometimes we say H equals $0.3, so we pay $0.3 per dollar on a dollar of inventory per year that we hold for 1 year. These two are equivalent, okay? Because what is 30% of $1? 0.3. So if H is given as a percentage, just multiply the percentage by $1 because that's the percentage you're going to pay on a dollar of inventory to get H in dollars per year. These are the units of H. So whatever H is, so this means that for $1 value of inventory, you spend $0.3 to store it or hold it for 1 whole year, okay? So you multiply H times the landed cost times the average inventory level. That gives you the holding cost or carrying cost in dollars per year. Why is it in dollars per year? Because H is in dollar per dollar per year. So the year comes from the units of H. Let's do an example. Let's say the average level of inventory of bread at a bakery is 150 loaves. Okay. The cost of bread is $2, so that's like our landed cost, $2. And the holding cost H is 40%. Another way to represent the 40% is 40% times $1, which is $0.4 if $1 of inventory is kept for 1 year. What is the annual carrying cost of bread? You just multiply HCl. H is 0.4. C is $2, and AIL, average level of inventory, is 150 loaves. So when we multiply these three numbers out, we get $120 dollars per year. Okay, because 0.4 times 2 will give us 0.8, and 0.8 times 150 will give us 120. Okay, so it's pretty straightforward calculation. So in the previous example, the average inventory level, AIL, was just given in the problem, is 150 loaves. This will not usually be the case. Usually we'll have to calculate the average inventory level as step 1. So usually in step 1, we'll calculate the AIL, which in this case was 150. Then step 2, we'll do this calculation. Okay. So AIL, we know, is the cycle stock, the average cycle stock, which is Q over 2, Q being the lot size, order size, batch size, the all terms for Q. This is how much we order each time we place the order, plus the safety stock. So Q is the ordering quantity or size of the order batch that arrives at the location where inventory is kept. Okay, so let's learn how to calculate safety stock, because if we know Q and we know safety stock, we can just divide Q by 2, add the safety stock, get average inventory level, and we're good. Now, safety stock depends on 2 things: the cycle service level and the demand during lead time. So this is a term you're going to have to learn to wrap your head around. Okay, DDLT, demand during lead time. What it means is that if you have time, okay, and you take a chunk of time, which is your lead time wide, L days. Remember, L is our lead time, and L is composed of 2 things, is P plus T, where P is the processing time the supplier takes, T is the transportation time for the supplier to you. Whoever your supplier is, your supplier could be another company, your supplier could be another facility, right? Whatever the lead time for you is. So during this lead time, what can the demand be? So demand is obviously going to be going up and down during the lead time. So I can, look at the total demand or the sum of the demand during lead time. So I can have D LT, that's demand during lead time, okay, like the average level of that. And then I can also calculate, because this demand is variable, I can also calculate the standard deviation of demand during lead time, okay. So the demand during lead time in general is going to be a variable quantity. Different when you say that your lead time is, let's say, from March 1st to March 15th, you're going to get some demand value during lead time. But then for the same 15 days of lead time between April 15 and April 30th, you may get a different value of demand during lead time, because demand is random. It's variable. And the lead time itself could be variable. So sometimes the lead time could be 15 days. Sometimes the lead time could be 13 days, 12 days, 15 days. Okay. So we are going to use the demand during lead time. We're going to model it as some probability distribution. So usually we use normal. So we're going to say, okay, it's normally distributed with some mean level, give it some mean and some standard deviation. So we need this plus the service level, the cycle service level. And then you can calculate the average inventory level. Then you can calculate the safety stock, which will give us the average inventory level. Cycle service level is the probability of not running out of stock during an ordering cycle. In other words, the probability that safety stock will suffice against demand and lead time variation. Okay, CSL is often set by management based on risk tolerance, or it can be determined algorithmically to minimize inventory costs. It may be, there's another metric called fill rate, okay? And this is talked about in a different lecture, so I'm not going to go into it in detail. Oftentimes, management will have a fill rate target in mind. So we want our fill rate to be 98%, and then they'll pick the CSL, whatever CSL gives them a fill rate of 98%. So you have to be a little bit quite careful if the management is talking the language of fill rate, which is percentage of demand satisfied. So, we only have 2% lost sales. We satisfy 98% of our demand. If they give you a fill rate, then you can't just put in 98% into the formulas that we talk about here. You have to convert it to cycle service level, and there's no straightforward way. You can just assume a cycle service level. Let's say you assume cycle service level is 90%. Do your calculation, it'll give you a fill rate. Then if the fill rate is more or less, you adjust your cycle service level till you get approximately 98% fill rate. And Excel is easy to do. You can use like a goal seek command, okay? Adjust my CSL level until my fill rate becomes 98%. But anyway, for the purposes of this lecture, we're going to assume we know the cycle service level. Like management has told us, so we have a policy, we know the cycle service level that we need to set. So the demand during lead time is variable because of two things. Demand changes from day to day. It's not the same every day, and lead time is not constant. Okay. Remember, if demand and lead time are both constant, then we don't need safety stock. It's going to be 0. And then we can just go here and say average inventory level is Q/2 because safety stock is 0. But that's usually not the case. Usually both demand and lead time are variable, or at least demand is variable. So we're going to assume the demand during lead time is normally distributed. However, it doesn't have to be the case. You can use different distributions of demand and adjust these formulas for negative binomial or Poisson distribution and follow the same logic and do all of what we are doing with a different distribution for demand during lead time. Okay, we're going to use normal, assuming it's a reasonably good fit for demand during lead time, and using different distribution, a little bit of an advanced topic. I may cover it in future, but for the purpose of this course, we're going to just assume demand is normally distributed. If you understand the logic, and the logic will look the same, the formulas will kind of look the same, and you'll just have to know how to work with a different distribution to calculate, things like, what level gives you what is the level that demand can only be higher than that 5% of the time, something like that. So you need to be able to calculate that using whichever distribution you need to use. But in any case, for the purpose of this course, we'll stick to the normal distribution for now, for this lecture. So assume the demand during lead time is normally distributed with a standard deviation called SDL, where DL stands for demand during lead time, with a mean value of D times L. So D is demand per day or per unit time. Unit time could be per week, so demand per time period, usually a day, but could be a week. Okay, and lead time is the L is the average lead time, and this is average demand, by the way, average demand. And L is the average lead time in the same time units as D, in the same time units. So if small d is in days, L has to be in days. If small d is demand per week, average demand per week, L has to be in weeks. Okay. So let's say, a lead time was 9 days. So the first day my demand was, 4 point something, then 2 point something. So you can see my demand goes up and down. So that's one source of variability, right? This up and down movement of the demand around some average level. This would be D, and it goes up and below D on different days. But 9 would just be my average lead time. On average, my lead time is 9. Sometimes lead time would be 7 days. Sometimes it could be 11 days. You could have demand here that has to be added up. So if you add up these bars to get the demand during lead time, the total demand during lead time, you'll see that sometimes you're adding up 7 days or 8 days or 9 days or 10 days or 12 days or 5 days. You're adding up a different amount of days, and each day has different amount of demand. So this demand during lead time, which is the sum of these bars, is going to vary. Sometimes it's going to be a small number, sometimes it's going to be a big number. Okay. So that's what we're modeling by normal distribution and saying, okay, it's going to vary, it's going to have some mean, and it's going to have some standard deviation. Yeah. So the mean is easy to find of demand during lead time. The mean is just small d times L. Okay. And then we'll see how to find the standard deviation of demand during lead time. But if we do know the standard deviation for demand during lead time, then safety stock just becomes Z, which is the Z score corresponding to the cycle service level, times the standard deviation of demand during lead time. So Z times SDL. Okay. So how do we get Z? We simply use this Excel formula. In Excel, we type equals to indicate we're typing a formula, norm.s.inv. In parentheses, we type 0.95 if the cycle service level is 95%. So cycle service level is going to be a value, like a percentage value, usually between 50 and 100%, well, not 50 and 99%. And so whatever the value is, 75, 85, 88, 93, whatever that value is, divided by 100 to get it into a ratio, so 0.95, a probability. So 0.95 is a probability corresponding to 95%. And then use norm.s.inv. This will convert the standard normal distribution with this probability into a z-score. And that's the z-score you'll multiply by the standard deviation of demand lead time to get safety stock. Basically what's happening is what's shown in this picture. Okay, so this is the average demand we expect during lead time. And the cycle service level, if it's 95%, it says our safety stock should bring us to a level to some point such that the chance of being above the point, which is where you will have lost sales because you're above, your demand is more than all the inventory you have. So that's lost sale area. So the lost sale area should be limited to 5% because we want a 95% chance that we are not in the lost sale area. Here we are all good. Right? We're all good. We have enough inventory to cover demand. So in the all good area, we are 95% of the time, and only 5% of the time we fall into the lost sales region. Okay. So what's this level? Well, this level is given by the mean value plus Z times SDL. Yeah. And you would notice, what is this value? This has a name. This is called the reorder point, ROP, reorder point. This is what we said as a reorder point. And we place the reorder when inventory hits this level. And we can see the reorder point is made up of the mean demand during lead time and the safety stock. The mean demand is here, and this part right here is the safety stock Z times SDL. Okay. And so that's how we can find the safety stock. Now, all that's left to find is how do we get the standard deviation of demand during lead time. Okay. So let's look at that. We have formulas for that, so it's not a problem. Okay, so demand during lead time has the expected value. Okay, that's the average demand during lead time, which is small d times L, and then it has variations around the average. So captured by the standard deviation. So if you have constant demand and constant lead time, no variability in your system, the standard deviation of demand in lead time is 0, and you get safety stock of 0 because Z times 0 will be 0 because Z times SDL is your safety stock, right? So remember that your safety stock equals Z times SDL. So if SDL is 0, then safety stock will be 0. Now, if demand is variable but lead time is a constant, there's no variability in lead time, then SDL is simply standard deviation of demand, which will be given, or you can calculate if you have historical demand data, multiplied by square root of the lead time. Okay. And if the demand is variable and the lead time is variable, then standard deviation of demand during lead time will be square root of this whole thing, which is lead time times standard deviation of demand squared. Okay, which kind of comes from this part, because you could write this as L times SD squared, square root, right? This one. And then SD squared and the square root, you can pull SD out and take out the square, because square and square root cancel. So you can get SD times square root of L. But this LSD square is just this thing right here. Okay. If you pull the SD inside the square root. So there's variability coming from demand variability, plus there's variability coming from the lead time variability, which is average demand squared times standard deviation of lead time squared. You add both sources of variation up, and then you take a square root to get standard deviation, because remember, variation, you have to take a square root of variation to get the standard deviation. Okay, so that's the formula. Now, if the formula doesn't make intuitive sense to you, don't worry about it. Just, you have to know, write it down somewhere, keep a note, know how to do this calculation. Obviously, I'm going to give you an Excel template as well, which has the calculation built into it. Now, the interesting part is, that makes this whole thing easy. You should remember one formula, which is this formula. The other formulas are special cases of that. How? If lead time is constant, anything that's a constant, okay, anything that's a constant, constants have variance of 0 and also standard deviation of 0. So anything that's a constant, you zero out the standard deviation. So if the lead time is a constant, SL goes to 0, this term drops out, and you get LSD square root, which is SD times square root of L. You get this case if you make the lead time constant. What if we make the demand and lead time both constant? Then this goes to 0 because SL is 0. SD 0, this goes to 0. Square root of 0 is just 0. So SDL is 0, which goes back to here. So you can derive both of the other cases just by remembering this one case. And whatever is a constant, you put the standard deviation to be 0, which is by definition. Okay. So really it's just one formula that you need to know. Okay. So again, the same formula is listed again for your ease. Safety stock is Z times SDL, which is standard deviation of demand during lead time. And then you have 3 situations for SDL. Everything is fixed, no variability is 0. Variable demand, fixed lead time is SD times square root of L. Variable demand, variable lead time, it's L times SD squared plus D squared times SL squared, whole thing square root, where L is your average lead time in days, SD is standard deviation of demand, and you're squaring it. Small d is demand per time period, the same units of time period as the lead time, but it's demand per day or demand per week, whatever units you're using, that's squared, times SL is standard deviation of lead time squared against the same time units, days or weeks, whatever you're using. And then you square it and you multiply these things out, add to these things, and then you take a square root of the whole thing. Let's do a self-test question. You're in a situation where demand and lead time are constant. Okay, so that means SDL is 0 basically. It's this case right here, the top row. Okay, the ordering quantity is 48. That's your Q. What is the average inventory level? So remember, average inventory level, AIL equals Q over 2 plus safety stock. Because SDL is 0, because everything is fixed, nothing is variable, this will be 0. And so AIL will just be Q over 2, and Q is 48. So what is Q over 2? 48 over 2 is 24. Okay, so that would be your average inventory level in case everything was fixed, there was no variability in demand or lead time. Now we're going to solve this bakery example in this presentation to learn how to do all these calculations, and then we're also going to see how to use our Excel template to do this. So this is data. We will not use all of the data for calculating inventory carrying cost, but all data is here, so you can refer back to slide 25 whenever you see the bakery example to get the parameters. So there's a bakery, they order in batches of 500 loaves from the supplier. So this bakery kind of sells bread. Maybe they're not baking their own bread. Maybe they bake other stuff. So they get 500 loaves from a supplier. Demand per day is on average 60 loaves, standard deviation of 30. So demand is variable. That means we will have safety stock because demand and lead time both would have to be fixed for it to have a zero safety stock. But now we're going to have safety stock. Supplier takes 4 days to prepare the order with a standard deviation of 1 day. So sometimes it's 4, sometimes it's 3, sometimes it's 5. Transportation from the supplier to the bakery takes 3 days with a standard deviation of 2 days. So transportation is very unreliable. Sometimes it can take 1 day, sometimes it can take 5 days. So on average, the lead time is going to be the processing time plus the transportation time, or 7 days. That's L. Average lead time is 7 days. Inventory carrying costs are 40%, and the purchase cost of a loaf of bread is $2. Now, when you do have lead time like this broken apart, so you have L equals P plus T, where this is your processing time, this is your transportation time, then standard deviation of L is going to be the standard deviation of the processing time squared plus standard deviation of the transportation time squared, the whole thing square root, okay? Because you just add up, this is a variance, you add up the variances and then take a final square root to get a standard deviation when you have different components. That's making some assumptions, but you don't have to go into all the probability theory. This is a reasonable kind of approximation for this lesson. Now, what do we have here? We have standard deviation of 1 day for SP, so it's going to be 1 squared, plus standard deviation of 2 days for the transportation, that's going to be 2 squared, square root, so that's going to be 2 squared 4 plus 1 5, 5 square root, that's going to be the standard deviation of lead time, and average lead time will be 7 days, 4 plus 3. Okay, so all that is given here. Inventory carrying costs are 40%. The purchase cost of a loaf is $2. Transportation costs are 40 cents per loaf. So the landed cost C is going to be C naught, the purchase cost, plus the transportation rate at our bakery, once it's at our bakery. So that's going to be $2 plus 40 cents, or $0.4, or $2.4. That's going to be our landed cost. Cycle service level is 95%, and now we have to do, all of our calculations. So let's calculate the inventory holding cost. So we already talked about lead time is P plus T, processing time of the supplier plus transportation time. That's going to be 4 plus 3, 7 days. That's the average lead time. Obviously, it varies because both the processing and the transportation times vary. So the standard deviation of lead time will be the processing time standard deviation squared plus standard deviation of transportation time squared, the whole thing square root. So this is a symbol, but it really means the square goes all the way wherever these brackets end. So the whole thing is being square rooted, okay? The final answer inside there. That's going to be, 5 square root, which is 2.236. Now, standard deviation of demand during lead time, SDL, is going to be given by this whole thing. Lead time average times SD squared, which is 7 days L. SD is given in the question, because if you go back, this is your SD, standard deviation of demand per time period, which is 60. Right? Small d is 60 and SD is 30. Okay, so L is 7 times 30 squared plus demand per time period squared, which is 60 squared, times SL, which we just calculated here, squared. Now try to keep 3 or 4 decimal places for intermediate calculation and only round up your final answer to whatever the question tells you. Usually I ask of students in questions to round the final answer to 2 decimal places. That means the intermediate calculation must keep more than 2 decimal places, otherwise you'll have too much round off error. So keep 3 or 4 decimal places in the intermediate calculations. Okay, but you'll be doing it in Excel anyway, so you don't have to worry about rounding. Excel will take care of all of that for you. So when you do this calculation, standard deviation of demand during lead time, which is SDL is going to be 155.88. Value of Z is just calculated by equals norm.s.inv of 0.95, because CSL was 95% in the question, which gives us 1.645. So safety stock is going to be Z times SDL. So it's going to be 1.64 times 5 This is a typo. Okay, so 1.64 times 155.88 will give you 256. So 1.645 times 155 will give you 256.407. Now, once we have the safety stock, we calculate average inventory level. That's Q over 2 plus safety stock. Question told us Q was 500, so just 500 over 2 plus 256.407. That gives us 506.407 as the average inventory level. If it seems overwhelming, don't worry. Once you put the formulas in Excel, it's just plug in, like putting in the numbers, the parameters, and Excel does the calculation kind of for you. So inventory carrying cost is H times C times AIL. The question told us H was 0.4 or 40%. Landed cost was $2 paid to the supplier plus 40 cents paid to the transportation company, or 2.4 total, times the average inventory level of 5 or 6. That gives us $486.15. So how do we interpret that? On average, in the bakery, if you go in on any particular day, on average, and you measure the inventory in the bakery, and you do it for multiple days, and you take an average, the average inventory level of loaves in the bakery is 506.407 loaves. Okay, and then the total money that we are spending to hold or carry this much inventory level is $486.15 per year. So, about $486.15 every year we spend to carry or hold this level of inventory in the bakery of bread loaves, just for bread loaves, okay? Okay, so that was a very involved calculation. The other ones are much easier. So we've done the hardest part, okay, the inventory carrying or holding costs. Ordering costs are much easier to calculate, so we can just breeze through these. Okay, so ordering costs are proportional to the number of orders placed in a year, because each time you place an order, you incur a fixed cost associated with placing an order called S. So S is going to be dollars per order. So the units of S, okay, S is in dollars, not per year, per order. Each time you place an order, you spend S dollars. And then how many orders we place in a year, that's given by the annual demand, capital D. Remember, this is your annual demand, not small d. This is a year's worth of demand on average. So how do you get that? You take small d. If this is per day, you multiply it by 365 days in a year. Okay, or if the store is open 6 days a week for 52 weeks, then it's going to be small d times 6 times 52 weeks. This, by the way, is 312. So you're working 312 working days times d. That'll give you annual demand. If small d is demand per week, then you multiply by 52 weeks to get big D, annual demand. Annual demand is weekly demand times 52 weeks, or daily demand times 365 days, or daily demand times number of working days the shop is open for, things like that. So you can calculate big D. Okay, and then Q is your ordering size or batch size. So D over Q is how many orders N you will place in the whole year. For each order, you pay S dollars. So how much do you pay over the whole year? You pay S times number of orders, which is D over Q. So S times D divided by Q is your ordering cost in dollars per year for the whole year. Easy peasy lemon squeezy. So let's do an example. The same example we had on slide 25, same numbers. So Q is 500, which we need to know. And we are given daily demand, okay? But we're open 6 days a week. So we're going to multiply 6 days a week by 52 weeks in a year to get our days on which we actually have demand, because when we are closed, we have zero demand. That's 312 days times 60. This is our annual demand. Okay. And then we do S is given in the question is fixed ordering cost is $5. Each time we place an order with our supplier, we spend $5. So it's $5 times the annual demand divided by Q of 500. So over the whole year, we spend $187.20 placing orders, because we're placing a lot of orders. Like annual demand is this much. Each order is like, a small fraction of that. So we're placing orders, way more orders than once a month. We're placing several orders a month, right? If it was, let's say, 19,000 then it would be, we would be placing about 38 orders in a year. So you're placing a little bit, maybe like 37 something orders in a year, right? So that comes out to more than 3 orders per month. Okay, so you place more than 3 orders per month. Some months we place 3 orders, some months we place 4 orders, and over the whole year, our ordering cost, because each time we pay, we have a cost of $5 to place an order, this is our ordering cost for the whole year. Okay, that is done. See, that was easy. Okay. Let's take care of out of stock costs. See, if you have empty shelves, you have no inventory, people can't buy your stuff, and you're losing sales. So that's loss in profit. Now, to determine the out of stock cost, we need to figure out how many units on average will be short by when we do have an out of stock, when we do have stockouts, okay, during a replenishment cycle. Okay, because some replenishment cycles we don't have a stockout, we are short 0 units. Some replenishment cycle we do have a stockout and we're short certain units. So we can figure out that the expected amount will be short by this number called EZ. Okay, it's called the unit loss integral, but you need to know what that is. The reason it's called the unit loss integral is you need to use, it's usually calculated using some integration or calculus on a probability distribution, but you don't have to worry anything like that. You're going to put in an Excel command and Excel will do it for you. This is the Excel command. You're just going to type this into Excel. You're going to replace the Z by the Z-score. Okay, what is the Z-score? Remember we found the Z-score doing equals norm.s.inv, and we gave it the cycle service level of 0.95. Usually we, could be 90%, then we do give it 0.9, could be 85%, give it 0.85, whatever that is. So this gives you the Z-score. Whatever Z value you get, like for 95%, you get 1.645. Okay, you plug that in place of Z, you put in 1.645. Notice there's false here, there's true here, so you have to keep it like that. And this Z multiplied by Z is also going to be 1.645. Okay. So, using this Excel function, you can calculate the value of EZ. So in any replenishment cycle, EZ times SDL, which you've already calculated for your inventory holding cost, remember, because safety stock is Z times SDL. So if you calculated your holding cost and average inventory level and stuff, you already have calculated Z using this function, and you've already calculated SDL. So you just take those values. You take SDL, you convert the Z into EZ using this formula, okay, and then you multiply SDL by EZ to get the expected stockout units per order cycle. This number here is a number of units. How many units do you lose sales of? 5 units is your lost sales, 3 units, 4 units on average. Okay. Once you get that, you're almost home. Because once you have the average units you are stocked out by in a replenishment cycle, you just need to multiply it by the number of replenishment cycles in a year. Number of replenishment cycle is number of orders you place in a year. Okay. So that is simply N equals D over Q. It's the same N, the number of orders you use in the ordering cost calculation. In the ordering cost calculation, you already use D divided by Q to calculate number of orders. Same thing, D over Q, that's number of replenishment cycles. So D over Q, which is N, number of replenishment cycles, times the number of units you're short on average in a replenishment cycle will give you total number of units you're short in a year. This number times this number when you multiply them together. So now you have total number of units you are short in a year, that you had demand for it and you didn't have inventory for them. So then you multiply that by K. K is the cost of lost sales or back orders, whatever is happening for your situation, lost sales or back order. And the units are dollars per unit. How many dollars of money do you lose if you have 1 unit of lost sales? That's K. So when you calculate the expected units of lost sales over a whole year, multiplied by K, you convert to a dollar value. That's your out of stock, or also called lost sales cost. Lost sales cost or out of stock cost, they're both the same thing. D over Q, you know the annual demand, you know your order batch size. K should be given in the question. It's usually the gross profit lost on a sale, or maybe you add a little bit more extra because you have reputation lost. When there's a lost sale, customer doesn't like it, customer service loss, and then you multiply by this. Right? So that's the formula. Let's do an example to solidify these concepts. Okay. So again, the same bakery example. We're going to assume we lose $1 each time a unit of bread is not sold due to being out of stock. Okay. Cycle settler is the same as before. It's the same example, 95%. Lead time is P plus T, which is 4 plus 3 or 7 days. Daily demand is 60. Standard deviation of daily demand is 30. Q is 500, same as before. Annual demand, same as before. 60 times 312 days in a working days in a year, 18,720. Standard deviation of demand during lead time, same as before, 155.88. Z we get from Excel using the formulas given previously, norm.s.inv of 0.95, we get this. And then EZ we calculate using this formula right here, this long formula. We just plug and chug, put Z 1.645 in it, and type in this formula, and it'll give you an EZ of 0.02089. And now it's just, simple math. Annual demand D 18,720 over Q, which is 500, that's D over Q, times K, the money you lose on a lost sales, that's $1, times SDL, which is 155, standard deviation of demand during lead time, times EZ, which is 0.02089. When you multiply all this together, you get the out of stock costs at $121.94 per year. So that's how much money you're losing by not having, because you run out of inventory sometimes. Okay, that's how much money you lose. Now the K of $1 each time, I think is a low. It's just an example. In real life, you might want to use a bigger K, because each time the customer comes and you don't have bread, it increases the chance they'll switch to a different bakery. And if they switch to a different bakery, the customer lifetime value is lost. They're not going to be your customer anymore, right? So you might want to think about what value of K to use in real life. Okay, so we're almost done with our inventory cost calculation. Remember, we had 4 components: ordering cost, inventory holding or carrying cost, lost sales or stock out cost, and then the last one was pipeline inventory cost. That is the cost of inventory while it's in transit from the supplier to us. Okay, so here we have to remember that right till now, we've been using the C to calculate our inventory carrying cost. That's the C. Remember HCAIL? This was the formula for inventory carrying cost or holding cost. Okay. And in that, we use the landed cost C. But while the inventory is in the truck in transit, we usually have not paid the transportation rate R yet. So for pipeline inventory cost, using the landed cost is not fair because the R dollars have not been paid yet. So the inventory inside this truck still only cost us C0 dollars, the value we paid to the supplier. When the truck delivers it here, then we'll pay the transportation company. And here, the cost of the same inventory will go up to be the landed cost C0 plus R. But while it's on the truck, the cost of inventory, each item just cost us C0 dollars. So for pipeline inventory costs, we're going to use C0 dollars for pipeline inventory costs. Okay. And for carrying costs in our distribution center or retail store, we're going to use the landed cost. Okay. Because that's what makes sense. Obviously, you have to understand the logic and not be like, oh, that's what usually happens, so that's always going to happen. What if you prepaid for transportation? What if you'd already paid for transportation in advance when the stuff left the supplier's facility? Then you would use landed cost for pipeline inventory cost as well. What if supplier had included the price of transportation? The supplier was responsible for transportation, and also the supplier owned the inventory in transit. So it's not even your inventory. Then you have no pipeline inventory costs because you have no pipeline inventory. The supplier owns the inventory in transit. If, the truck has an accident and inventory gets lost, suppliers is liable. They're going to give you another fresh batch. Okay, so it depends on the situation on how you calculate the pipeline inventory costs, whether you're going to use landed cost or the price paid to the supplier, whether you even have any pipeline inventory costs, because you may not even own the inventory in transit. We're going to do the usual case. Usually you're going to be owning inventory in transit because supplier is responsible till their door, and then you and your transportation company are responsible. And usually you pay the transportation company after they complete the delivery. So the usual case is that we do have pipeline inventory costs because we own the inventory while it's on transit, and the inventory is valued at C naught, the price paid to the supplier, not at the landed cost. Okay, so we're going to do the usual case now. Note, if supplier agrees to own inventory during transit, that are your terms of trade, then pipeline inventory will be zero for you, but then the supplier will own the pipeline inventory and the supplier will calculate the pipeline inventory cost. Pipeline inventory cost formula is really straightforward. It's H times C naught. Remember, it was HCAIL for inventory carrying cost. So instead of AIL, we're going to have a different number, but it starts off like HC. So we're going to use C naught because we're not going to use landed cost. We haven't paid the transportation company yet. So H times C naught, very similar to that formula. And then, the average inventory on the pipeline is given by D, annual demand, multiplied by just the transportation time, not the whole lead time. A lot of students make this mistake. They say, okay, lead time is 7 days. They plug and chug the lead time into the pipeline inventory cost. No, because the lead time has two parts. The supplier took time to process and make the order ready, the P, processing time, and then T, the transit time or transportation time. Pipeline inventory is inventory during transit. While the supplier is processing the order, it supplies inventory. It's not your inventory. So you don't plug and chug in the lead time L, only the transportation time part of the lead time T. Okay, so T over 365, that is the fraction of the year the inventory spends in transit, times annual demand, because every single piece of annual demand spends some time, comes through this transit path. So that's multiplied by H times C naught. Okay. Remember, landed cost is C equals C naught plus R, where R is the transportation cost per unit. So this is the C naught you use here, the money you pay the supplier. You don't add the transportation cost yet, because usually you pay the transportation company after the goods have been delivered. So that's the logic we are assuming. Okay. So let's do it for the bakery example. Annual demand we calculate a bunch of times is 18,720, 60 loaves of bread per day we sell. The bakery is open 6 days a week for 52 weeks. 60 times 6 times 52, 18,720 loaves of bread is our annual demand. That's how much we expect to sell annually. Then the pipeline inventory cost will be H, which is 40% or 0.4, times C naught, which is $2, given on slide 25. If you don't remember where the 2 is coming from, it tells us that the supplier charges us $2 per loaf of bread, times the annual demand, 18,720, times the transportation time, which is on average 3 days over 365, and it's going to equal to $123.09 per year. Remember, this number has to be 365 and not working days, because usually when transportation companies work and they're carrying product, they don't take days off. They're like, the truck is moving, whether it's Saturday or Sunday or Monday. So you don't use the days your bakery is open in this. We don't divide T. You divide T by 365. You don't divide T by the days your bakery is open, because even if bakery is closed, the truck is still moving. Okay. Whereas for annual demand, if you are given daily demand, you have to multiply daily demand by the number of days the daily demand applies to, and average daily demand does not apply to when you're closed. So here we have to use working days for annual demand. Okay, so annual demand is always going to be daily demand times whatever days you are selling on. If you're selling, if you're only open 1 day a week or whatever, 2 days a week, then you do it like that. Usually I'm not too fussy. Usually I'm going to just tell you, okay, this is the daily demand, and you're open 365 days a year, or you're open 250 days a year, or 312 days a year, or I tell you 6 days a week times, and 52 weeks in a year, and so you can calculate annual demand. Do not use this number in the pipeline inventory formula. Pipeline inventory formula, you always just use 365. Okay? So just remember that. Anyway, that's going to be coded. The formula is coded into the Excel template as well. And so you don't have to worry if you're using the Excel template, or you can type it out into Excel and then reuse it. Okay, so let's look at total inventory costs. This is the whole formula that we studied. Ordering cost, D over Q, that's number of orders N times S. Inventory holding or carrying cost, HC times AIL. AIL is just the thing in brackets, Q over 2 plus safety stock, which is Z times SDL. SDL, you're given the formulas on how to calculate depending on whether only demand is variable or demand and lead time are both variable. Or if nothing is variable, then this whole term goes to 0. Z times SDL is 0. Plus out of stock cost, D over Q, number of replenishment cycles, times K, the cost of one unit being out of stock, times SDL times EZ, which is the average number of units out of stock during a replenishment cycle, plus the pipeline inventory cost. The whole calculation, we add all these four terms together, gives you the total inventory cost for you. This is not total cost of every single thing in the supply chain. It's only the total inventory cost in dollars per year of this setup. Okay, where you have inventory in a distribution center or retail store, its purchase price is C naught, you spend R dollars on transportation, landed cost is C, which is C naught plus R, and then this would be the cost of inventory at that location for whatever item you're doing this calculation for. Let's go back to our bakery example. All these calculations are already done for you in the lecture, so you're just putting them together. Ordering cost, $187.20 per year. Inventory holding cost, also called carrying cost, $46.15 per year. Lost sales cost, $121.94. Pipeline inventory cost, $123.09. You sum all these four numbers up, you get total inventory cost in dollars per year of $918.38 for this bakery. Okay. Now we can do this in Excel. So this Excel file is provided to you on Canvas, and you can download it. And in the Excel file, you have these input areas colored as blue. So this is all the blue cells are input you have to specify for the model. And then the gray cells are intermediate things that calculates itself. So gray cells have formulas, don't change the gray cells. The only gray cell you should need to change sometimes is the row 36, Q EOQ, because this cell here, which has 500, is supposed to have your order size. Now I could ask you a question two ways. I could say, calculate the order size using the EOQ formula. Okay, and then if you do that, then the Excel template will automatically calculate the EOQ value for you and put it here. Okay, the EOQ value, I believe, for this example is less than 500. Okay, but in this question, the question told you we are not ordering by the EOQ quantity, maybe because the EOQ quantity only fills half a truck. We want to order full truckload, something like that. We are ordering 500 loaves of the bread at a time. So we just delete the formula in this cell and just hard code in 500 to solve this bakery example. Okay, and you can see we got the exact same value. We got $918.38 per year total. $918.38 total inventory cost dollars per year. Our four components of cost: carrying holding cost, $486. Inventory ordering cost, $187. Lost sales or back order cost, $121. Pipeline inventory cost, $123. So the Excel template gives you the exact same values that you get from manual calculation. You just plug into the blue cells. The only gray cell you might have to change is the Q, the order quantity, because if you're not using EOQ, you have to hard code the value in. And notice it's giving you the average inventory level, 506.41, exactly what we calculated. It's giving you SDL. It's giving you number of ordering cycles. Remember, it says a little bit less than 37 point something ordering cycles. And then it's even giving you the fill rate. With a cycle service level of 95%, you get a fill rate of 99.35%. You're satisfying more than 99% of the annual demand. Okay? So it does all that. And then it also multiplies all the transportation rate of 0.4, right here, per unit, $0.4, with the annual demand D to give you the money you're spending on transportation. So right now, with this bread loaf example, you're spending more than $7,488 on transportation, and you're spending a little bit less than $1,918 on your inventory costs for the bread. Okay, And so you can see that in this logistics system, in this simple bread setup, the transportation costs dominate, but then the inventory costs are also like, not zero, they're significant, they're also there. Okay. So you can open the Excel file, the inventory template, plug in these values in the blue cells, do not modify the gray cells, they have formulas in them, except that this gray cell will have the EOQ formula. This example doesn't use EOQ, so you have to manually type in 500 here, and then you get all of these values. Try it for yourself and be happy that you don't have to do this calculation manually, but you need to understand what's happening, right? Because what if in a question I said, okay, supplier owns inventory in transit, so you have zero pipeline inventory costs. Then you have to go here and from this total, subtract the pipeline inventory cost because that's zero for you. Supplier is paying for that. And then you have to give me an answer without the pipeline inventory cost. So you have to know how this Excel works. So I've explained over the whole lecture, the whole logic, the formulas, how these things work, so that you can use the Excel file smartly and not make mistakes where the real life situation I gave you is a little bit different, and you can't have pipeline inventory costs because supplier owns inventory, for example. So you have to kind of do those adjustments. But usually just plugging and chugging in this template will solve, almost all problems you'll see in this course. And so it's really easy, makes it life easy for you. Okay, let's do a self-test question. Let's say average daily demand D increases. Everything else remains the same. Variance of demand remains the same. Lead times remain the same. Everything else remains the same. Which of the following is true about safety stock? It increases. It decreases. It remains the same. It increases if lead time is variable, and it stays the same if lead time is constant. Cannot be determined with the information given. A little bit of a tough question, okay? Because if you know safety stock equals Z times SDL, and this can be 0, this can be standard deviation of demand times square root of lead time, and this can be the more complex case of lead time times standard deviation of demand squared plus demand squared standard deviation of lead time squared. Okay. So if it's 0, if everything is fixed, demand is fixed, lead time is fixed, like there's no variability. So even if demand goes up, but it has no variability now, it's going to take the new value, then safety stock will neither increase nor decrease. It will remain the same. But if it was this case, here if demand goes up, but SD and L don't change, safety stock again remains the same. But if it's this case, then here's the demand. If D goes up, then SDL would go up, which means safety stock would go up. Okay. So if lead time is variable, safety stock will increase. But if lead time is not variable, in these cases, safety stock will stay the same. So D is the most correct answer, because the answer depends on whether you are in this case, in one of these two cases, or you're in this third case. And what's the difference between the third case and the first two cases is the lead time variability. If lead time is variable, you're in this situation. So demand going up will make your safety stock go up. But if your lead time is not variable, then demand going up will not affect your safety stock, it will stay the same. Okay. So hopefully, that made sense. Now let's talk about transportation cost. And this is very easy, very straightforward. Transportation costs can be complicated. Depending on the order size queue, we can estimate total transportation expense per order, because you can ask somebody who's a transportation analyst, okay, I need to order Q pieces from this place to this place, like move them from this place to this place. This is their volume, this is their weight, because transportation costs often depend on volume and or weight and or volume, or both, or one of the two. And so they will tell you, okay, this is how much it's going to cost you. So if it costs you, let's say, I don't know, $500 to move Q units here to there, you can divide $500 by Q to convert the transportation cost to a per unit cost. So per unit, you're paying this much for transportation. So we call that R. R is the transportation rate to transport one unit. Usually, if you only transport one unit, you'll not end up paying R, you'll end up paying a lot more. but we are calculating R based on Q. Okay, so we are saying given that order size is Q, then what will be our transportation cost? Then we divide them by Q to get a rate, and then transportation rate is whatever the cost the analyst gave us for transportation of this batch over Q. That gives us dollar per unit transportation cost, okay, which is R. Okay, so our transportation cost is going to be R, which is the cost we pay per unit, times how many units we're going to transport in the year. We're going to transport capital D units on average, which is the annual demand. So annual demand times R gives us the transportation cost for the whole year. $0.4 in the bakery example times the capital D, the annual demand, $7,488. Now, this is an important note to know that the economic order quantity EOQ does not factor in transportation cost economies of scale. Okay, so the EOQ quantity can sometimes be a very inconvenient quantity to transport. What if your order size that you get from EOQ fits in 1.3 containers, a 1 full container and a 1/3 of a container? That might be really bad because now you can ship a full container and then the other container is going to be mostly empty. So you might say, okay, I'm either going to round it down to 1 container or round it up to 2 containers because I want to ship either 1 container of goods or 2 containers. I don't want to ship 1.3 containers of goods. Okay. Or it may be that the Q that you get from EOQ formula is 50% of a truckload quantity or 60% or 70%. And you have some empty space left, might as well just ship the whole truckload to save on transportation cost per unit or transportation cost per pound rather than just ship out some somewhat empty truck. Now, so we can adjust Q. So often when we do logistics, we are not just going to use the EOQ quantity as an order size. We're going to adjust it up or down to get a convenient quantity that gives us some transportation economies of scale. And that makes sense because the cost that EOQ minimizes, order cost versus carrying cost, that total cost curve in practice is usually really flat around the optimal value Q. So if you move Q up or down, you're not giving up much in terms of those costs, and you might be saving a decent amount on transportation costs. Okay, so we usually do that. Usually we'll round up Q or round down Q to a truckload or container load type of quantity so we can have economies of scale in transportation. Okay, so finally we get to the meat of this presentation, and it's really brief, don't worry. I know we've been talking for a while. Logistics decisions and cost trade-offs. Why did we do this whole thing of calculating ordering cost, inventory holding cost, lost sales cost, pipeline inventory cost, calculating the total inventory costs? Why did we go through this whole bother? You're going to see now many logistics decisions impact transportation time and then hence lead time. Okay, so if they impact transportation time and lead time, that's going to impact our inventory costs, and we need to figure out what that impact is to know if this logistic decision, what is the the impact of this decision on costs. So let me give you an example. So my total logistics cost in the on what we've been studying so far is inventory plus transportation costs. Obviously, there's material handling costs and some other stuff which we've not included, but the main costs that are going to be impacted by logistics decisions are going to be the transportation cost and the inventory costs. Okay. Let's look at some cases, and you should be able to work through this because by now you understand this formula. Let's say procurement team, they select a faster but more expensive transportation option. Transportation time T reduces, but transportation rate increases because you have to pay more for this faster transportation. Okay, so if transportation time reduces, this T goes down. Okay, so pipeline inventory cost reduces. Okay, This has lead time built in it, has a lead time in it, because lead time goes down, SDL goes down. So if lead time goes down, then SDL goes down. So wherever you have SDL, this quantity will go down. This whole term will go down because SDL is, excuse me, because SDL is reduced. SDL here is also reduced, so safety stock will go down. Okay. And there's no impact of lead time here. Okay. So to summarize for number one, let's call it number one. For number one, this goes down, safety stock goes down, lost sales cost goes down, okay, because SDL goes down. Pipeline inventory cost goes down because T goes down. So I got three costs going down here on the inventory side. But transportation cost goes up because R goes up, because usually for faster transportation, we have to pay more. So now you can do the trade-off. You can see how much does transportation cost go up. You can calculate with the new R times D. That's the new transportation cost. Okay. And then what's the new inventory cost? You can do this calculation with the new lead time and the new transportation time. And because this cost is going to go down, inventory cost will go down. So inventory cost will go down and transportation cost will go up. You can see if the increase here is paid for by the decrease here, or if this goes up much more and this doesn't go down as much. So you can then you can see that trade-off in action. You can actually put numbers around the trade-off. Transportation cost increase of whatever many dollars or 10% leads to an inventory cost decrease of this much. Okay, so very important. This is what was our goal in the beginning of the presentation. I told you this is our goal, and now you can do it in your very easy to do it with this Excel template. Okay, you will reduce T. Let's say now T is on average 2 days. Maybe standard deviation also went down to 1 day. Okay, and this R maybe it went up to 0.45. Okay, so you can make these changes and see how much does this change and how much does this change, and you can see the trade-off right there. By just plugging and chugging and changing some numbers in the Excel template, you see exactly the transportation and inventory cost trade-off. So that is really cool. Okay, and you can do that now. Okay, let's look at some other logistics decisions. So let's look at number two. So this was number one. Number two, right? And you can see this happening commonly, right? You pick a faster transportation mode. Happens all the time. Or a slower transportation mode the other way, and it's cheaper. So R goes down and your transportation cost is less, but because transportation takes longer, now all your lead time is longer, and then all your inventory costs are going up because you need more safety stock. Procurement selects a different supplier that is further away and has a greater processing time. So procurement moved to a different supplier. Maybe their procurement cost, they're saving some money, but for you in the logistics side, okay, now processing time has gone up and transportation time because they're farther away. And P, they both went up. So L went up by a lot. If lead time goes up, right, and it's probably going to cost you more to transport because it's farther away. So R went up, okay. T went up, so pipeline inventory cost went up. SDL went up because lead time went up, so this cost went up, this cost went up. So you have 1, 2, 3, 4 factors of your cost have gone up. Ordering cost will stay the same. And then you can go to procurement and say, okay, what's so good about this new supplier? How much money are you saving? Because my costs are going up by exactly this many dollars per year. Are you going to save this many dollars per year? If not, please don't do this to me, right? So you can have that conversation because now you can quantify the logistics cost increase. Okay. Supplier starts giving lower priority to your orders. So P, the processing time with the supplier increases. That means lead time will go up. This can happen, maybe supplier found a better customer, they're ordering more from the supplier, and you're no longer a priority customer. It happens, right? Just life, deal with it. So P goes up. Processing time, which means lead time goes up because lead time is just P plus T. If any component of lead time goes up, P or T or both go up, lead time will go up. Lead time goes up, this goes up, safety stock, lost sales cost goes up. T did not go up, so that would not go up, right? So this would not go up in this case, okay? And transportation cost would also not go up because nothing changed there, Just the processing time went up, but it's the same distance we're moving stuff. Okay. Okay, so just your safety stock went up and your lost sales cost went up because of supplier increasing their processing time, which affected your lead time, but not the transportation time. Only the lead time. The pipeline inventory will stay the same because transportation transit time is the same, distance is the same. Procurement selects a larger order size to benefit from full truckload, so Q goes up. And also R decreases because if you're shipping full truckloads, it's going to be cheaper per unit. So R falls. Let me actually clear the ink and start again. So R will fall because the full truckload discount. It's not a discount, but you're shipping full truckloads of economies of scale. Okay. And Q went up. So ordering Q increases. So Q increases here. So D over Q as a whole decreases. So ordering cost went down because you're ordering fewer times a year. This Q went down. Okay, so your inventory holding cost went down. This Q went up, so this D over Q went down. So your lost sales cost went down because you have fewer replenishment cycles now. Okay. Yeah, and your demand is the same. Demand didn't change, D is the same. And that's it. So your ordering cost goes down, inventory holding cost goes up. So I made a mistake. Let me fix that. Q is going up. Only D is going down. So I apologize. That was a mistake. Q goes up. So this cost, let me color it differently. This cost will move up, whereas ordering cost will move down because you're dividing by Q, and Q is going up, so D over Q goes down. This cost will go down. Okay, and R will go down. So you have R going down, lost sales cost going down, ordering cost going down, but your inventory holding cost goes up, and then you can compare the cost benefit analysis. The costs that go down, do they dominate, or the cost that goes up, does that dominate? What is the net benefit? You can do that calculation, and easily you can go back to your Excel template, plug in the new Q, plug in the new R, and see what happens to the costs. Okay, so this is what is the cake you need to eat. This is the fruit of this whole labor. That when you make these logistics decisions or procurement changes something, you can go to your Excel sheet, you can calculate the impact on inventory costs, you can see which costs are changing, how much are they changing, and you can do the cost benefit analysis. Okay. So this is what you need to be able to do, and especially it's pretty easy doing it with the Excel template that is provided. Okay. So hopefully this lecture is going to help you. And obviously when you do some problems, you can do the bakery example yourself, do some practice. You'll be right at home doing this sort of analysis. So that is it. We have now learned how to do this. Look at logistic decisions and calculate their impact on inventory costs.